Hello everybody, welcome to Chemistry 101, where we talk about chemistry. Today's topic with regards to electrochemistry is calculations in redox reactions. After this video is done, you should know how to write and balance equations for redox reactions in acidic and neutral solutions by using half-reaction equations obtained from a standard potential table. Also, you should know how to perform calculations to determine quantities of substances involved in redox titrations. To balance a half reaction, balance all the species involved except for oxygen and hydrogen. Balance oxygen, then balance hydrogen, and lastly balance all the electrons. Let's take a look at example 1. Balance the following half reaction. Here we have a dichromate ion, which by the looks of it has lost electrons to form the chromium ion. First, we need to balance all the species involved except for oxygen and hydrogen. These species are called the major species. Here, only chromium is the major species, and since there are 2 chromium ions on the left side, we need to make sure that there are 2 chromium ions on the right side as well. Next, we are to balance the oxygen. As you can see, there are 7 oxygen molecules on the left side. To make sure that we have equal amounts of oxygen on the right side, we do so by adding 7 water molecules. Next, we are to balance the hydrogen. Since we added 14 molecules of hydrogen to the right side when we added the 7 molecules of water, we now need to balance the equation by adding 14 hydrogen ions to it. Next, we are to balance the electrons. As you can see, the right side has a total charge of positive 6. The left side has a total charge of positive 12. That means that to balance the equation, we must add 6 electrons to the left side. To predict the net equation of a redox reaction, we need to identify all entities present in the solution, and then determine which are oxidizing agents and which are reducing agents. The strongest oxidizing agent and the reducing agent present are then identified, based on their position on the redox table. Write out half reactions, and if the number of electrons in the half reactions are not equal, multiply one or both by their lowest common factor. Once the electrons are balanced, the equations can be added to produce a net equation. Let's take a look at example 2. If solid copper is placed in nitric acid, what is the net ionic equation? The entities present are copper, hydrogen ions, nitrate, and water. The reducing agents are copper and water. Of the two, the stronger reducing agent is copper. The oxidizing agents are nitrate and water, and nitrate is the strongest of the oxidizing agents. The half reactions found on the redox table are 2 molecules of nitrate plus 4 hydrogen ions plus 2 electrons, giving us dinitrogen tetroxide plus 2 molecules of water. At the same time, we have solid copper, which loses 2 electrons to form the copper ion. We then balance the electrons, but since there are equal electrons on both reactions, we do not need to change anything. We then combine the 2 equations to give us a net equation of 2 molecules of nitrate plus 4 hydrogen ions plus solid copper, 2 dinitrogen tetroxide plus 2 molecules of water, and copper ions. It is important to note that nitrate and hydrogen ions combine to form the strongest oxidizing agent, which is above the strongest reducing agent. The reaction is therefore spontaneous. As you may have noticed, redox reactions in acidic solutions are very similar to normal solutions. This is because balancing hydrogen ions will automatically produce an acidic solution. Let's take a look at example 3. Given that the following reaction occurs in an acidic solution, predict the following net equation. Well, we have manganate, which reacts with solid copper to form the manganese ion and the copper ion. We have the skeleton half reactions taken from the redox tables. By balancing the oxidation, we have, and by balancing the reduction, we have To balance all entities, balance the electrons from both half reactions. Since our first half reaction has 5 electrons and our second has 2 electrons, the lowest common factor is 10 electrons. Therefore, we're to multiply one by 2 and the other by 5. This gives us 10 electrons on both sides. Hence, the electrons cancel, leaving us with the net equation of to predict redox reactions in basic solutions. Balance the half reactions following the same steps as usual. After balancing the half reactions with hydrogen ions, neutralize them by adding equal numbers of hydroxide ions to both sides. This should be done as the last step in the balancing process. Let's take a look at example 4. Given that the following reaction occurs in a basic solution, predict the net equation. In this equation, we have dichromate plus dicarbon tetraoxide, giving us the chromium ion and carbon dioxide. Now we can break them into two half reactions. We have dichromate into the chromium ion and dicarbon tetraoxide into carbon dioxide. We balance the major atoms, giving us 1 molecule of dichromate to 2 molecules of chromium ions. We also have 1 molecule of dicarbon tetraoxide to 2 molecules of carbon dioxide. Now we can balance the oxygen atoms on both sides. In the first half reaction, we have 7 oxygen atoms on the left side. Hence, we need to add 7 molecules of water to the right side. In the second reaction, as the oxygen atoms are already balanced, there's no need to change anything. Next, we proceed to balance the hydrogen atoms with hydrogen ions. Since we added 7 molecules of water to the right side on the first half reaction, we must balance the equation by adding 14 hydrogen ions to the left side. Then we balance the charge with electrons. Notice the two half reactions have electrons on opposite sides. One should be oxidation and one should be reduction. Next, multiply the half reactions so that the number of electrons on both sides are equal. This way they can cancel out. The balance equations should not have free electrons floating around. For this equation, the lowest common factor is 6 between the two half reactions. Hence, only the second reaction needs to be factored. Add the reactions together, canceling out any additional hydrogen ions or water molecules. A quick check of charges revealed that there are indeed a charge of positive 6 on both sides. Now, if we were dealing with acidic solutions here, we will be done by now. However, since this is a basic solution, we cannot have free hydrogen ions lying around. To neutralize the hydrogen ions, add equal ratios of hydroxide ions to both sides. The side with the hydrogen ions will neutralize to water. The side without the hydrogen ions is left with 14 additional hydroxide ions. Notice that there are 14 molecules of water on one side and 7 molecules of water on the other. These can cancel out, leaving us with 7 remaining water molecules on the other side. A quick check of ion charges show that we have a negative 8 charge on both sides. Now that you're starting to understand the way redox reactions work, let us put them to use by performing redox reactions with them. Stoichiometry can be used in redox reactions to determine the quantities of substances in a way as it is used for normal chemical reactions. Establishing stoichiometric ratios in net ionic equations allows one to use concentration equations to find unknown values. A titration is an analytical procedure commonly used to determine the concentration of a sample by reacting it with a standard solution. In redox titrations, the titrant is a strong oxidizing or reducing agent. As the titrant is added to the sample, a redox reaction occurs until equilibrium is reached, and then the reaction can no longer proceed. Two strong oxidizing agents that are often used in redox reactions are solutions containing permanganate ions or dichromate ions. This is because they both change color as they are reduced, indicating that an equivalence point has been reached. Let us take a look at example 5. A 25 milliliter sample containing iron chloride is titrated with a 0.100 molar solution of permanganate. If it takes 21.05 milliliter of permanganate solution to reach an endpoint, what is the concentration of the iron chloride sample? Let's take a look at our skeleton equation. By balancing the skeleton equation, we get, and that leaves us with a net equation of Now we can calculate the moles of manganate used. Since the moles of manganate and the moles of permanganate is a 1-to-1 ratio, we can use the volume and concentration of the permanganate given to us by the question to solve for how many moles of manganate are used in the stoichiometric equation. Now we can use the molar ratio from the net equation to find the moles of iron. As you can see, it takes 5 moles of iron to react with 1 mole of manganate. That leaves us with 1.0525 times 10 to the power of negative 2 moles of iron. Now we can determine the concentration of the iron chloride sample. Since we have determined how many moles of iron are used to react with the manganate, and the molar ratio of iron to iron chloride is a 1-to-1 ratio, we can use the previous calculations to determine the concentration of iron chloride by finding it in moles per liter. Since we have used a 25 milliliter sample of iron chloride, we must divide the number of moles found from the previous calculation by 25 milliliters. That leaves us with a final concentration of iron chloride to be 0.421 molar. Since the lowest number of sig figs in the question was 3, our question will end with 3 sig figs. Let's take a look at our final example. A solution containing I2 was titrated to endpoint using 50 milliliters of 0.25 molar Na2S2O3 solution. How many moles of I2 were present? We can derive the products with the following data. The products are iodine ion and S2O4. We can balance the skeleton equation with S2O3 plus H2O, giving us S2O4 plus 2 hydrogen ions plus 2 electrons. We also have I2 plus 2 electrons, giving us 2 iodine ions. We can then derive the following net equation. The molar ratio of I2 to S2O3 is 1-to-1. Hence, to find the moles of S2O3, we can multiply 50 milliliters by 0.25 moles per liter, giving us 3.75 times 10 to the negative 3 moles. Since the moles of I2 to S2O3 is a 1-to-1 ratio, the number of moles of I2 present is also 3.75 times 10 to the negative 3 moles. I hope this video has been helpful and that you are now more confident with your understanding of electrochemistry. Thank you for watching. Bye.